So, welcome to the second lecture in cryptography on information theoretic security and the one-time pad. So, as promised, we're going to be talking about Shannon's idea of perfect secrecy. So, the basic idea is this. The ciphertext should never reveal information about the plain text, right? So if all you get to see is the ciphertext, then you should learn absolutely nothing about the plain text, right? But we have to, of course, formally explain what does information about the plain text actually mean. So of course we have a definition. A cipher ED over the triple KM and C has what's called perfect secrecy if the following is true. And I'll explain what this means here in a minute. Okay, so it just so happens that for every two messages, M0 and M1 in the message space, the only requirement is that the two messages have the same length, and for every ciphertext in the ciphertext space, for every pair of messages and for every ciphertext, it had better be the case that if we ask what is the probability that encrypting M0 with K gives C, how likely is it if we pick a random key that we encrypt M0 that we get C? And that probability should be the same as when we encrypt M1. So if all an adversary A has is C, then he has no idea if the plain text or the ciphertext came from M1 or M0. So this means here the probability of encrypting M1 and getting C is exactly the same as the probability of encrypting M0 and getting C, right? So these two probabilities are the same. The probability of getting C is equally likely whether M0 is being encrypted or M1 is being encrypted, right? Where K is uniform in the key space, right? So I'll explain here what this notation means in a minute. Right, so where the distribution is over the distribution on the key, right? And I'm using this here to denote the fact that K is a random variable that is uniformly sampled in the key space K. So then we ask, of course, it begs the natural question, what does it mean that Shannon's two probabilities are the same? So it says that if an attacker intercepts a particular ciphertext C, then in reality, the ciphertext, the probability that it is the encryption of M0 is exactly the same as the probability that is the encryption of M1, right? So just to recap, so we're going to restate this definition. So the definition means if I'm given a particular ciphertext, so given particular ciphertext, I can't tell where it came from. So the attacker can't tell if the message is M0 or M1, right? And this is true, of course, for all M0 and M1, right? So not only can an attacker not tell if it came from M0, M1, he can't tell whether it came from M2, M3, M4, etc., because all are equally likely to produce the ciphertext C, right? So even so, the most powerful adversary can learn nothing about the plain text just from the ciphertext, right? So basically, what this proves is that there exists no CT-only attack on a cipher with perfect secrecy, right? So no CT-only attack exists on a cipher with perfect secrecy. But that doesn't mean, of course, that other attacks don't exist, right? Other attacks may be possible. So then the question becomes, can we build ciphers that actually have perfect secrecy, right? So that leads to a lemma. So the OTP has perfect secrecy, right? And here is the proof. So for every message in every ciphertext, the probability that the encryption of M under a key K, so the probability that it is equal to C, the probability of a random choice of key, so that is, so the number of keys K in key space such that if we encrypt is equal to C, it's all going to be over the size of our key space. So the number of keys that map M to C is divided by the total number of keys, basically, is what this is saying here. So if we choose a random key, that key maps M to C. Right? And this is constant. Right. So if this is the case, then by definition, then all M0 and M1 and for all C, this probability has to be the same because the denominator is the same, the numerator is the same, which is this constant here. For this is always the same for all M and C, right? So now suppose that we had a cipher that for all messages and for all CTs, it so happens, yeah, right, that we look at the number of keys K in our key space such that the number of keys that map M to C, we suppose that this number happens to be constant, right? So if this property is true, then we say that the cipher has perfect secrecy, right? Well, what can we say about this quantity for the OTP? So question, what can we say about this quantity for the OTP, right? So in other words, how many OTP keys are there that map this message M to the ciphertext? How many keys are there such that M XOR K is equal to C, right? So we let M exist in the message space and C exist in the ciphertext space. So how many OTP keys map M to C, right? So this should be immediately obvious, of course, that the answer is 1, right? So the answer here is 1. And so for the next lecture, we are going to be going over, of course, another proof, stronger proof, of course, that despite having perfect secrecy, it doesn't mean that the OTP is a secure cipher to use. So we'll go a bit more into depth about that.